We have previously derived the expression for the effective free energy per unit spin in the mean field approximation in the Ising model. So this is the expression that we derived starting from the Ising model. It seems more complicated than it actually is, so it's not too complicated. From the Ising model, you make the mean field approximation, and then you define the effective free energy and also the effective free energy per unit spin, and after some simple considerations one can derive this expression. At this point we consider the so-called Landau's approach. So this was an approach proposed by the famous physicist Landau, and the famous physicist considered this parameter m, which is also known as the order parameter. And basically what we are going to do is we are going to expand these natural logarithms with respect to m. So the natural logarithm of 1 plus x, or in general you can also have minus x by simply changing the sign of x, this is equal to x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4 plus dot dot dot. Therefore, if you also want to write the natural log of 1 minus x, or in that case m, you simply have to change the sign of this as well. So you have minus x squared over 2 minus x cubed over 3 minus x to the 4 over 4 plus dot dot dot. And if you replace these expressions there, it is just algebra, what you find is that f of m can be written like this: minus t natural log of 2 minus b times m plus 1/2 t minus j times q m squared. Then the subsequent term is 1 over 12 t m to the 4th plus higher order terms. Now at first let's consider the case when the magnetic field is equal to 0. So this is the first consideration that we're going to do. At first let's assume that b is equal to 0. And let's also drop this constant term which makes nothing to our physics, in particular to this function. It is simply a translation that we are not really interested in. So we are really interested in this part. But if we set b equal to 0, this term is also, of course, 0. So we only have these two terms plus, if you want, higher order terms. So the approximation is better and better as m becomes smaller. So these terms can be neglected with respect to these two here. Anyway, if we set b equal to 0, we have actually two possibilities in the shape of the function f of m. So f of m will be a function of m. So we want to plot f of m, but if t is greater than j times q, and this j times q is called the critical temperature Tc, so let's assume that first t is greater than Tc. So if t is greater than Tc, then the only minimum value of the function is at m equal to 0, and then it behaves like this. So the function increases for values of m that are greater than 0 or less than 0. The physical meaning of this, when the temperature is greater than the critical temperature, is that the temperature will cause some jiggling of the spins in a random manner. Therefore, since they will become more random, they will also give a zero contribution to the magnetization. And that's why we get that the equilibrium value for the magnetization, or the minimum value in this case, is 0. The minimum value is important because it will be the natural value of the system. Then what happens if we decrease this temperature and it will be less than Tc? So let me sketch it in red. What happens is that actually the function f of m will have two minima. One positive minimum and a negative minimum. And they are perfectly symmetric if b is equal to 0. And how do we find the values for these two minima? Well, it's very simple because we just have to take the derivative of f with respect to m and set it equal to 0, knowing that b is equal to 0, so we just have to take the derivatives of these two terms, and we have to set them equal to 0. Now, if you do this, and you call the minimum value for m, you just call it m0, you find m0 equal to the square root of 3 times tc minus t divided by t. And remember that in this case we are considering T less than Tc, the critical temperature. So we have found an average value for the magnetization, so this is the positive value, but we also get a negative value which is exactly symmetric, so you also get minus the same thing, so you get plus or minus the same thing. Let me stress that this value here, these two values, with the plus and with the minus, are only precise close to the point t equal to tc. So it is true that t is smaller than tc, but we are very close to tc because we are neglecting these higher order terms. Okay? Then another important thing that we have to mention is the following. So remember that in general, when we consider the generic expression for f of m, which is this one, so before expanding the natural logarithms, well, we have found that if we calculate the derivative of f of m and with respect to the magnetization and we set it equal to 0, we get an equation of the following form: m equal to the hyperbolic tangent of beta, which is 1 over t, if you want, times j times q times m. In this case, remember that b is equal to 0, so we found the expression also with the magnetic field, but if we set the magnetic field equal to 0, this is what we get. And j times q is equal to tc. Simple as that. You can also write this expression in another form, so tc over t times m is equal to 1/2 natural log of 1 plus m divided by 1 minus m. So basically this is just the inverse hyperbolic tangent of m. So I have taken the inverse on both sides of this expression, and this is how you can write this expression. Now, this is also useful to understand what happens when t is greater than tc. So if t is greater than tc, we expect that the only solution to this equation here is m equal to 0. I'm going to get back to this in a moment, but let's wait a little bit more, because I also want to consider the condition t less than tc. If t is less than tc, I'm going to rewrite this equation in the following way. So I'm going to solve for t. T is equal to tc times 2m divided by natural log of 1 plus m divided by 1 minus m, like this. Now, if we consider this function here, so we consider t as a function of m, and I want to plot the following graph. M, and here on the x-axis I have t, but I have expressed t as a function of m. So if you want, you can sketch this graph. You can also sketch it like this if you want, tm. So t in the ordinates and m in the abscissa, but it's just up to you. What you get is the following behavior. So when t is equal to 0, well, what we get is either plus 1 here or minus 1 here. And you can also check this kind of behavior from the equation here. So if t is very close to 0, we get a divergence here. And in order for us to get a divergence here as well, we need to let this m go to minus 1 or go to 1 in order to get a 0 here, and therefore we would get a divergence here as well. But anyway, you can sketch this expression, and what you get is something like this. So you will get that at some point, in particular Tc, you get that the magnetization would be 0. And for t greater than Tc, the value for the magnetization, we expect it to be equal to 0. So we set it equal to 0 because this function here will not allow us to get a value for t which is greater than Tc. This graph tells us that if we, for example, start at the point where the temperature is greater than Tc, and we decrease the temperature, and remember that the magnetic field is set equal to 0, then at some point below a critical threshold, a temperature, Tc, we get that the material will get some magnetization. So it can either go in this way, so the magnetization can either be positive or negative. The system will pick one of the two ground states, m equal to m0 or n equal to minus m0. So remember that when we are below the point Tc but very close to Tc, we have found that either this value or this value here, these two values, satisfy the following condition. When we are very close to the point t equal to Tc,